Hello everyone, welcome to my channel. In today's video we solve a practical problem where we need to calculate instantaneous water particle velocities and accelerations at a particular point below seawater level. We will do calculations for a range of options when, for example, we have wave crest passing above that point or wave trough passing above that point. I will do calculations in Excel that when I change input data, all the calculations updated dynamically. I also present my results in a graphical forms. Therefore, when I change my given data, the graphs are also updated dynamically. Before we start, I would like to ask you, if you find this video useful, please subscribe to my channel. Okay, so let's start. In this video, I will calculate instantaneous water particle velocities and accelerations at a point below still water level. I will do these calculations in Excel and will create a dynamic spreadsheet where if I change the input data, all the calculations and my graphs are updated automatically. For example, this could be useful if I want to give different set of data to different student groups or to different students. First, I will start with describing the problem, then I will describe the methods used, and after that I will do calculations in Excel. In our problem, we have a wave with period of 11 seconds and height of 6 meters that is traveling in the water with depth of 21 meters. We need to calculate the magnitudes and directions of the water particle velocities and accelerations at a point which is 10 meters below still water level under the wave crest. So when above the point of interest, we have wave crest, under the wave trough, and also when we have zero crossings, which is downwards zero crossing, means between crest and trough, and upward zero crossing between trough and crest. Now I will describe the method and then we'll do calculations. In our methods, we will use a range of equations to calculate velocities and accelerations. And we will calculate both horizontal velocities and horizontal accelerations, as well as vertical velocities and vertical accelerations. Depending on wave type, we will have to use different equations. And wave type is defined based on the ratio of water depth divided by wavelengths. So we will need to calculate the wavelengths and then calculate the ratio depth divided by wavelengths, and depending on the value, we will use set of equations either for intermediate waves, deep waves, or shallow waves. These equations are obtained from velocity potential function for linear wave theory. I don't show derivations, but this is how these equations are derived. First of all, the velocity potential function for linear wave theories is derived equation, and then equations for individual velocities, horizontal and vertical, and also individual velocities accelerations are written. And in these equations we have symbols, which is 8, which is wave height, wave period is t, k is the wave number, which is defined as 2 pi divided by wavelengths, and sigma is the circular frequency, which is defined as 2 pi divided by wave period. Expression in brackets, which is kx minus sigma t, changes from 0 to 2 pi. Depending on what is specifically above the point of interest. For example, if we have crest, we know what this expression in brackets is equal to. For example, when we have wave crest above the point of interest, the expression in brackets is equal to 0. When we have wave trough, expression in brackets is equal to pi, and so on. And we also can estimate the water surface elevation depending on the particular part of the wave above the point of interest. For example, when we have wave crest, our water surface elevation is equal to amplitude. And amplitude here is just the height of the wave divided by 2. Okay, let's start to do calculations. To speed up calculations, I have already prepared a table with all the relevant headings, and I also prepared some graphs where I will do calculations. And as soon as I do calculations, my graphs will show the calculated values. On this spreadsheet, I show the problem and I also show my given data. Because the spreadsheet is dynamic, input data are being read from the problem spreadsheet, which is from here. Therefore, as soon as I replace the given data with any other data set, then my calculations are updated dynamically and my plots are updated dynamically. To start calculations, I need to calculate the wavelengths, and I always start with calculating the wavelengths for deep water. For deep water, the wavelengths depends only on the wave period and is equal gravity multiplied by wave period in power 2 divided by 2 pi. Therefore, we calculate gravity 9.81 multiplied by wave period in power 2 and divided by 2 pi. So I open bracket, multiply by 2 pi and close bracket. My wavelength is 189. Now I need to confirm if indeed I have deep water wave. And I do this by calculating the ratio of water depth divided by wavelength. And this is equal 0.11, which is within this range. And this is the range for intermediate waves. Because for deep waves, this ratio should be greater than 0.5. In my problem, it's 0.11. Therefore, I need to use this set of equations to calculate velocities and accelerations. I will just copy these velocities and accelerations equations and paste them on my spreadsheet, and it will be in the same order I will do calculations. So horizontal velocity, horizontal acceleration, vertical velocity, and vertical acceleration. I will just pay them here for reference and I will do calculations. And because I'm displaying the data not only in a table, my calculated data, but also on graphs, which you can see on the right hand side, which don't show anything yet, but as soon as I will calculate, there will be information shown. I did this in advance just to see visually my results. And I would need for this to calculate water surface elevation because I would like to see my wave as well. And to calculate water surface elevation, I need the values under these brackets, which is kx minus sigma t. And we know that when we have the crest above the point of interest, this is expression under brackets is equal 0, then pi over 2, then pi, and then 3 pi over 2. And the elevation when we have crest is equal wave amplitude, and here is wave amplitude negative. Therefore, I will just calculate this and see if indeed I have this wave water surface elevation. So this would be equal 0, then this would be equal pi divided by 2, and this would be equal to pi, and this would be equal 3 multiplied by pi and divided by 2. And now I can calculate the water surface elevation as wave height divided by 2. I will be dragging formula to the right, therefore I need to fix this cell where wave height is, which is F2, by pressing F4, and then multiply by cosine, and cosine would be of this number. Therefore, when we have crest is 3, and then we have 0, then minus 3, and 0 again. And this is my nice wave. So crest, 0 crossing, trough, and 0 crossing again. And now I need to calculate my velocities and accelerations. To do this, I would need to calculate my wavelengths for intermediate water wave using full equation. And here we have wave lengths on both sides, therefore I will use solver to calculate this. I will need to start with trial value, for example 180, and now I have to calculate my wavelengths using this equation, which is equal d water wavelengths multiplied by hyperbolic tangent and open bracket, and we have 2 multiplied by pi multiplied by d and divided by trial value lambda, and close the bracket. And this is 118, so obviously it's quite far away from the trial value. I will use solver, which you can find using data tab, and here you would need to use solver. As you can see, it's not shown. If it's not shown, you just go to file, add-ins, options, and then you have add-ins, and here we have solver. Click go and we check the solver and click OK. And now solver should be shown on the data tab. It takes a little bit of time. And now we have the solver. So to calculate this, I go to solver and I set my objective, which is my formula where I calculate the wavelengths, which would be cell B5. And by changing the cell value, which is my trial value, which is B4, and I need to put my conditions. I already have this, but anyway, I will just delete this and then insert this condition again. And my condition would be that my trial value should be equal to the calculated value. And now I can solve and keep the value. So my wavelength is 139.4. And now I'm ready to do calculations. Just before I do this, I would like to calculate the wave number, because I would need to have my wave number to calculate these ratios, hyperbolic cosine divided by hyperbolic sine, because I decided to calculate these ratios to make this equation simpler separately. And I will calculate them here. So my wave number is equal to multiplied by pi and divided by wavelengths, which is here 139.4. So this would be my wave number, which is 0.05 radians per meters. Therefore, now I can calculate my hyperbolic cosine divided by hyperbolic sine. So equal, and we have hyperbolic cosine, open bracket. So we have k multiply, now open bracket again, and in brackets we have z, which is minus 10, plus d, and close the bracket, and now close the bracket again, and now divide it by hyperbolic sine, and in brackets we have wave number multiplied by water depth, which is this cell, which is G2, and now close the bracket, and this is my value. Here we have roughly slightly different equations, so what I will do, I will just copy this equation and paste them in this cell and change just instead of hyperbolic cosine to hyperbolic sine, because the rest is the same, and this is my value. So now I can do calculations of velocities and accelerations. As soon as I calculate the values, those values will be shown on the graph on the right. I'll start with horizontal velocity, so equal pi multiplied by wave height, which is 6 meters, divided by wave period, 11 seconds, and now multiply by the ratio hyperbolic cosine to hyperbolic sine, which I will be reading from this cell, and also multiply by cosine of kx minus sigma t, which I will be reading from the row I calculated, which is row 8, and close the bracket. Before I press enter, I would like to fix all the values which I would need to fix if I want to drag the formula to the right. And this would be my wave period, press F4, would be my wave height, and wave period, press F4, and also my ratio of hyperbolic cosine divided by hyperbolic sine, press F4. And now I can drag the formula to the right. And I show my calculations on the plot on the right, that this would be updated dynamically if I change my input data. On the top plot, I show the values of horizontal velocity and vertical velocities, but on the bottom plot, I show the values of accelerations. So I drag the formula, and these are all my values are shown. So here we have positive velocity, negative velocities, and this is velocity equal to 0. And now I can calculate acceleration, horizontal acceleration, using the formula. So equal 2 multiplied by pi in power 2 multiplied by wave height divided by wave period in power 2, which is in power 2, and now multiply by ratio of hyperbolic cosine to hyperbolic sine, which is again from here, and now multiply by sine, and in brackets we have kx minus sigma t. So sine, open bracket, kx minus sigma t, close the bracket. Now again, before I press enter, I would like to fix the values which I would need if I want to drag the formula to the right. So this would be again my wave height, which is F4, my wave period, which is press F4, and also my ratio of hyperbolic cosine divided by hyperbolic sine, press F4. And this is my acceleration, which is equal to 0 when we have water crest above the point. And these are my values of acceleration, which are shown on the bottom plot. I will just drag them a little bit higher, that you can see them both fully. Now I'm ready to calculate the value of vertical velocity, which is my pi multiplied by wave height, which is again F4, divided by wave period, again F4, and now multiply by the ratio of hyperbolic sine to hyperbolic sine, which I already calculated. Press F4 and multiply by sine, and in brackets we have our kx minus sigma t, and close the bracket. I already fixed all the values, so I can press enter, and now I can drag the formula. And these are my values. And again, I also show my values of vertical velocities on the plot. And finally, I need to calculate vertical acceleration, which would be equal minus 2 multiplied by pi in power 2 multiplied by wave height, and I fix it, F4 divided by wave period in power 2, and multiply by the ratio, which I already calculated, F4, and multiply by cosine, and again I read this from those values and close the bracket. And finally I drag them and I show my accelerations here as well. So all is calculated, and let's see how it's updated if I do change my data set. Obviously, if I change my data set, all the calculations are updated automatically except the solver. I will need to do the solver again. Okay, let's try. So I will check, for example, taking this data set and just replacing it here, paste special and paste the values. And now everything is updated. Obviously my wavelength is not the same, so I need to do it still intermediate water wave, but I need to update the value here using solver. This is the only calculations I would need to do. And just click solver. It's updated, and now everything is updated and all the calculations are now related to this data set. I hope you find this video useful, because this could be just a small part of another problem, because here we calculated instantaneous velocities and instantaneous accelerations. If you know instantaneous accelerations and velocities, you can calculate instantaneous forces, such as drag forces, inertia forces, and also total forces using Morrison equation. Therefore, this could be just a small part of a bigger problem. I hope you find this video useful. Goodbye!